So how do you simplify root 50? Well, I'm glad I wrote these numbers down. How do you simplify a root? What's the process? You definitely have to look at your list of square numbers to do it.
Let's see whatever is between 50, so 64, and then go down and divide it.
Yeah, you start wherever the number would be, so 50 is here-ish, and then you start moving to the left until you find a number that divides 50. So 50 divided by 49 is a decimal, 50 divided by 36 is a decimal, 50 divided by 25 is a whole number, it's 2. So 50 divided by 25 is 2. So you rewrite that as root 25 times root 2. That's the product rule, that you can multiply a root times a root to get another root. And then you simplify the first one and you get 5 root 2. So that's how you simplify a root. All right. Well, thank you, folks. Let's keep going. Today is April 3rd. Hey, did anyone have an April Fool's joke pulled on them? No? Yeah. Nobody in the whole room? Wait, you think we're too old? We're old people? We don't do April Fool's jokes anymore? No? I don't know.
I got one.
You did get one?
Yeah.
Somebody did an April Fool's joke on you? Is it appropriate for class?
Well, yeah.
Oh, okay. Go ahead. What was it?
Well, yeah, it is. All right, so my ex, she said she was pregnant.
Wow, now that is quite a story.
And I was really scared.
Well, okay then. Along those lines, I was trying to brainstorm with my wife what's something we could do to punk her family, because her family was coming over. My wife is already pregnant. She's due in July. I told her for April Fools, we should tell them she's pregnant again. Don't really know what that means, but I looked it up later. Apparently, it is possible for a woman to become pregnant after she's already pregnant. It's called metaphytation. What? Yep. It has to be within the first couple weeks of pregnancy. You can actually get pregnant again. 2 separate kids, non-twins, simultaneously. Isn't that wild? Apparently, it's very rare. Okay, well then, that's it for April Fool's Day. I do have a joke for y'all today. Why did the bicycle fall over? Why did the bicycle fall over? It was too tired. All right. Well, here we were, folks. Isn't this where we were? We were on number 48, I think. Well, I realize the number is different and wrong, but we're roughly in this area in the late 40s. Did we already look at a couple of these, I think?
Yeah, we're on the 256.
We're on the 256? Oh, we're past this?
Yeah.
Oh, okay, great. Okay, are we on the problem that says the 4th root of 256 to the 4th?
Yeah.
Okay. Well, that's wonderful, folks. I know that I talked with you about the grouping strategy, so let's just review the grouping strategy. If we have 256 a to the 4th, in order to do the grouping strategy, you have to break this down into its individual constituents. So 256, if I finished my list of squares up here, you would have seen 256. Let's just finish my list so you can see it. Wait, 225, 256. There, so 256 could be written as 16 squared. So I could write it like this. I could write it as 16 times 16, and then a to the 4th. But that doesn't help me very much, because that doesn't give me we're looking for quadruplets to circle and take out. So if I just wrote it like that, I would not have a quadruplet. I'd have a 16, a 16, an A, an A, an A, an A. So that's not an ideal solution. I want to be able to take out quadruplets, like this quadruplet of A's. So instead, 256, you'll also notice, is a 4th power. So that's 1, 2, 3, 4 to the power of 4. And that's more ideal. So that's 4 to the power of 4, a to the power of 4. That gives me a quadruplet of 4s and a quadruplet of A's. And so I can take out 1 4, and I can take out 1 A. And the answer is 4A. So that's the grouping strategy, if you like it. Again, there's some playfulness here, right? Maybe playfulness is not the right word. There's some messing around. You kind of have to play with the numbers and see how you might want to rewrite 256. You could have even gone further and said that 256 was a power of 2. You could have said You could have said 256 is actually 2 to the power of 8 and a to the power of 4. There we go. 256 is also 2 to the power of 8. And so if I wrote this out using the grouping strategy, I would have had 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And now I can take out this quadruplet of 2's, and I can take out that quadruplet of 2's, and this quadruplet of A's. And now it'll give me a 2, and an A, which of course is still 2 times 2 is 4A. So the answer is the same, however you choose to rewrite 256. I didn't show you all those different ways to confuse you, but just to show that there's a variety of ways to approach the same problem. Eldon?
I have a question. So if it's to the power of 3, you would have to find it.
You mean the index?
Yeah.
Yeah, then you would look for triplets of things to take out. Yeah, and if it's to the 5th power, you take out quintuplets. If it's just to the 2nd power, you just take out pairs. Yep. Okay, well, that was the grouping strategy, folks. I don't know if you like the grouping strategy or not, but here's the official strategy, and that is to, I would still rewrite 256 as a power. You still need to do that. So I'm going to start right here. Let's say we're still doing the 4th root of, which one should we choose? 16 squared, 4 to the 4th, or 2 to the 8th?
4 to the 4th.
That's a tough one. I mean, 4 to the 4th probably is the most appropriate because we know that those are going to cancel out. But I'm going to go all the way to the prime factor. I'm going to go all the way to the prime factorization, which is 2 to the 8th, a to the 4th. So we have 2 to the 8th, a to the 4th. Now, who can remind us, what does this root index represent as far as a fractional exponent goes? What was the definition of the numerator and the denominator? Yeah, power and root. So the numerator is the power, and the denominator is the root. So whatever the root index is, that becomes the denominator of the fractional exponent. So essentially, where does this 4 go? Yeah, it just goes underneath both of those numbers, right? The 4 slips inside, and it becomes the denominator of both of those powers. So the result is that you have 2 to the 8/4 times a to the 4/4. And isn't that handy? The root index just slips inside the root and becomes the denominator of the powers. And at that point, we have 2 to the power of 2, a to the power of 1, which is 4a. I think that's ultimately what the textbook would like to see, probably what they'll demonstrate in my math lab. What if we had not rewritten 256 at all? What if we had not written 256? Then technically that's 256 to the power of 1, right? So then you would still just slip that 4 underneath each of those exponents, and the result would have been 256 to the 1/4 times a to the 4/4, which would have still been 256 to the 1/4 and a to the 1st. So if you had done that, how would you simplify the 256 to the 1/4? Well, not dividing it. It's a power. What's one way you could do 256 to the 1/4? The easy way.
Calculate.
On your calculator. You can just plug it into your calculator, and it would tell you the answer is 4. Well, yeah, I mean, that's it. You'd have to just plug it into your calculator. So try it out, folks. Is 256 to the 1/4 equal to 4? Just try plugging it in and seeing if it works.
Yeah.
Oh, good. Okay. All right. Well, 53 is just like it in terms of the grouping. So I'm going to leave that one for you folks. So let's move along and try something a little different. Everybody's favorite, the Pythagorean theorem. Folks, do you ever find the name Pythagorean to be a little unfortunate? Pythagorean. Because a lot of people stumble over the word Pythagorean. They say all sorts of different things. Wouldn't it have been great had it been Bob's theorem? That'd have been nice. Real simple.
Wasn't he Greek?
Yeah, Pythagoras was a Greek. And he didn't even invent it. Other cultures knew about the Pythagorean theorem long before he did, hundreds of years before he did, but we name it after him. So let's take a look. Find the missing length in the right triangle and simplify the answer if necessary. So first of all, folks, just make a formula. Let's make a formula right over here. Make yourself a little formula. I'm going to show you the traditional formula. The traditional formula is that you take your two legs that meet at the right angle, call them A and B, and the hypotenuse is called C. And then, of course, we all know the formula a squared plus b squared equals c squared. That's the traditional writing of the formula, where a and b are always the legs that meet at the right angle, and c is the hypotenuse. The thing is that a and b can be swapped. It really doesn't matter which one is a and which one is b. I could have just as easily written it down as b and a, and that would be fine. But what I would like to really encourage you to do is write down a second formula in which you call the sides L for leg, and H for hypotenuse. I like this formula a little better because then it just states that the leg squared plus the leg squared is equal to the hypotenuse squared. And then you're giving the Pythagorean theorem in terms of what it's actually talking about, instead of these arbitrary letters A, B, and C. So the real Pythagorean theorem is the leg squared plus the leg squared equals the hypotenuse squared. How do you know which two are the legs?
They make a right angle.
Yeah, they meet at the right angle. All right, so we have this first problem here. Well, your number is different from mine, but it says 12, 9, and C. So at least for this first one, folks, what I'd really like to see you do is go ahead and label L, L, H. Bring some conscious awareness to the fact that you're saying that's a leg, that's a hypotenuse. And then, for the same reason, go ahead and write down the formula, leg squared plus leg squared equals hypotenuse squared. If you prefer A, B, and C, you can use A, B, and C. I'm just recommending you try something different. Okay, so what do I plug in for my formula? Jonathan? What do I plug in for my first L?
12 squared
Sure, it could be 12 squared. And my second L?
plus 9 squared,
9 squared. And what do I plug in for my hypotenuse?
C.
c squared.
Yeah, you can plug in C squared. I mean, might as well use C because that's the letter they gave us. If you wanted to use X, you could use X. You could just go ahead and call that side X. Oh, sure, we'll go ahead and use C. So now we have 12 squared and 9 squared equals C squared. So now maybe you have these memorized. 12 squared is 144. And 9 squared is 81. This is one handy reason to have your list of squares out in front of you today, so you can see all your squares. And in this particular case, when you know both of your legs, it's just a matter of adding these together. So what is that? 225? Oh, good. What a nice number. So now C is being squared, so you square root both sides. And what is the square root of 225?
15.
Yeah, once again, that's on your square root or your square number line. So you can say that's 10 squared, 10, 11, 12, 13, 14, 15. So the square root of 225 is 15. Now, is it plus or minus 15? Yeah, the plus one. What's the minus 15 solution? What would you call the fact that C could equal negative 15? That solution is extraneous. Yeah, the solution is only 15. The negative 15 does technically work. Negative 15 does technically work. If I plugged in negative 15 and then I squared it, I would still get 225. So negative 15 makes the math correct, but it's, what did I call it before? Ridiculous? Silly? It's true, but it's nonsense. That's what I said before. True, but nonsense. Negative 15 makes the equation true, but it's nonsense. You can't have a length of 15, of negative 15. Okay. All right. Well, that was the only one like that. The next three, what's different about the next three problems compared to the first one that we did? Yeah, one of the legs is missing. In the first one, the hypotenuse was missing. In this one, the leg is missing. Do you think that will make a difference in the algebra?
A little bit.
Yeah, a little bit. It will change it a little bit because we are technically looking for something different now. So let's draw that together. We've got our triangle here. We know one of the legs is B, the other one is 15, the other one is 25. Again, if I were you, I would label these as leg, leg, hypotenuse. The two legs meet at the right angle. And then you could go ahead and write down the formula, L squared plus L squared equals hypotenuse squared. And then you plug in all of your numbers. Siobhan, what do I plug in?
Sorry, I wrote it different.
Oh, that's okay.
So it would be L squared plus 15 squared
Oh, now that's true. So you're just going to use the letter L to represent the leg? Because they gave us the letter B.
Yeah.
But that is fine, folks. You could use the letter B, you could use the letter L, you could use the letter X. That's totally up to you. So Siobhan, you just used L? Okay, I'll run with it, Siobhan. Let's do it. So the other leg that's missing, L squared plus 15 squared equals 25 squared. What did you do next, Siobhan?
You would do minus 15 squared both sides.
Now that's certainly true. You could subtract the 15 squared from both sides. How about we go ahead and square it first?
Okay.
What is 15 squared? And then 25 squared? 625? Is that what you guys want?
Yeah.
Okay, good. Okay, so now we subtract the 225. Oh, and that kind of works out nice because that's just 400. Yeah, and then you square root it, and L is plus or minus 20. Of course, we all know the minus part is extraneous. The leg can't be negative 20. So we would just say the answer is 20. Even though technically speaking, the number negative 20 would make the formula true, we know that that's nonsense. Okay, everybody, go ahead and try another one. Oh, and in fact, these all worked out nicely. The next two, the answer is going to end up being a root. So go ahead and do the next two problems and get yourself to the root answer. And then we'll talk about how to simplify that. Maybe you've already started the third one anyway. Yeah, go ahead and do the next two. And let's see what numbers you end up with. Oh, okay. You did it backwards. I didn't say two. Here, rewrite that. Come right over here. Let's root 147. And then you want to simplify by finding a square number. Okay, so I won't solve both of these completely up on the board, but for the first one, did you end up with b equals the square root of 147?
Yeah.
So the square root of 147 doesn't come out clean. What did it come out to as a decimal? 12 point something?
Yeah.
Yeah, that sounds right. 12, what'd you say, 12.3, Jennifer?
12.1.
12.1, yeah. But we can simplify this. So let's try simplifying it. Find 147 on your square number line, and then start moving to the left until you find a number that divides into it. What divides into it? 49 does. Now, that right there could be a laborious process. You know, it won't take forever, but you just have to sit there and take your calculator and start dividing. 147 divided by 144, 147 divided by 121, 147 divided by 100, 147 divided by 81. You just keep going until you find a whole number, right? And the good news is you don't have to start with 144 because obviously 144 is not going to divide into 147. You can go ahead and skip down to half of that number. So half of 147 is like 73. I can really start here and start dividing to the left. So 147 divided by 64, no. 147 divided by 49, yes. So we rewrite now. Let me get myself some room here. We rewrite it. Oscar, tell me how to do it. I rewrite 147 as what times what?
49.
Yeah, 49 times. Yeah. And then the root 47, or sorry, root 49 becomes 7, and your answer is 7 root 3. So that'll be your final answer, folks. You simplify the root 47 into 7 root 3. How about the last problem there. What did you end up getting for the root? For number 57, the answer was
32.
root 32? Well, I mean the original one. Yeah, so on the last one, you should end up getting the answer root 32, but that as well can be simplified. And so again, your strategy, I'm throwing something new at you today. I'm telling you, you can always go down to half of that number before you start to divide it. So if I go to where 32 was, which is here, and half of that number is 16, I can really just start dividing there. And as it turns out, 32 does divide by 16. So you get to rewrite it as root 16 times root 2, which is 4 root 2. And that would be your final answer. All right. So we have a couple word problems here to try. Both of them are still about the Pythagorean theorem. The first one says the length of the diagonal of a rectangle is given by d equals L squared plus W squared. Now why is that? I'm going to draw a diagram right here. I think everybody can still see right here. So it says the length of the diagonal of a rectangle is given by d equals the square root of L squared plus W squared. Where on earth did that formula come from?
They making.
The what?
They making it.
They make it up?
Yeah.
Well, that's true. They made it up. It's true. It's not just fiction. So where did that formula come from? What are we talking about again? The length of the diagonal of a rectangle. So everybody draw a picture real quick. Draw a rectangle. And a rectangle has a length and a width. So let's just, I'm going to arbitrarily call this one the length and this one the width. And it says the length of the diagonal is given by D. So now go ahead and draw in a diagonal and call it letter D. Does that seem like a reasonable drawing? Remember, our word problem process is to always start by drawing a picture. So we've got a picture, and they're saying where L and W are the length and width of the rectangle. So now what can I do with this formula? Or what can I do with the drawing?
Shouldn't the L and W switch?
Well, the L and W can switch or not. I mean, I typically think of this as width. But I think that's an arbitrary choice that everybody can make. So what can I do with these three letters if I wanted to make a formula?
You need to fill it in.
Fill what in? You mean the other sides?
No, the length and the width by whatever the problem is.
Oh, well, that's true. They are going to give us numbers, right? They're saying what's the diagonal if it's 70 long and 41 wide. But I'm still interested in the formula. Where did they get that formula from?
The area of the triangle, or there's a triangle.
L squared.
The area is a good guess. The area is base times height, so that would just be LW. And that would be a different formula. What are you saying, Rob?
It would be the L squared, just like the triangle.
Yeah, it'd be the Pythagorean theorem, right? Everybody take your diagram that you just made and do the Pythagorean theorem with L squared plus W squared equals D squared. L squared plus W squared equals D squared. Does that look like the formula they gave us? It looks like it. What's different? Yeah, first thing is they switched it and they wrote D squared equals L squared plus W squared. And then what did they do? They just square rooted both sides. So that's where they came up with their formula. The length of the diagonal really is L squared plus W squared, all underneath the square root. And what is this formula technically? Bob's theorem. Exactly right. That's just Bob's theorem. So, all right, so now that we understand where the word problem came from, now we just do the problem that they gave us. They said, what is the length of the diagonal if it's 70 long and 41 wide? So now you can just plug that in. So it's 70 long and 41 wide. And you'll want to very, very, very carefully plug that into your calculator. In your calculator, some of you will do square root parenthesis 70 squared plus 41 squared parenthesis. I think that will give you the right answer. Or you can always just try squaring 70, squaring 41, adding them together, and then doing the square root. So for about the last month or two, my calculator has been telling me that I'm low on batteries. And then yesterday, my calculator finally died. And I was like, what? Without any warning? And it's still dead.
You need a calculator?
Well, no, I'll just ask I'll just ask you folks what you got. So what was sometimes switching the batteries around in the compartments actually gets you a little more juice? I don't know why that works if I'm just making that up.
It does work.
Yeah, I think it works too. Well, it didn't work this time. All right, so what was the number under the square root? It's the square root of what?
6,581.
6,581? And does that actually square root? Oh, okay, so it comes out to a decimal?
Yeah.
What's the decimal, Patty?
81.1.
81.1. Now, a big question would be, does 6581 simplify? Woo. Yikes. How would we know if it simplifies? I mean, yeah, you could start by cutting that in half and then start dividing by square numbers. We don't even have a list that goes up to 3,000. So that would be a very tricky task to find out if that's simplifiable. And are they asking us to simplify it? No, they say round to the nearest tenth. So they're asking us to approximate it to a decimal. They're not asking us to simplify it. So you really only have to simplify if they actually tell you to simplify. Okay, number 59. Where did they, well, it says the length of the diagonal of a box is given by d equals L squared plus W squared plus height squared. Where did they get that formula from?
The same.
Yeah, it's still the Pythagorean theorem. As it turns out, the Pythagorean theorem is true in higher dimensions. So in two-dimensional space, the Pythagorean theorem would be a squared plus b squared equals c squared, where you've got length, sorry, it'd be length and width equaling the hypotenuse. But if you go up to 3 dimensions, length squared plus width squared plus height squared is still equal to the diagonal squared of 3-dimensional space. And if you go up to 4-dimensional space, it'd be length squared plus width squared plus height squared plus, a lot of people refer to the 4th dimension as duration. Duration squared, that still would be equal to the diagonal squared. So the Pythagorean theorem is actually true up to as many dimensions as you want to go to. That's just a random little known fact. So in this case, that's all they're doing. They're saying now we're in 3-dimensional space and they still want to know the diagonal cutting across a box. So I'll let you guys finish that problem because it's just a matter of plugging in the numbers. Junior?
The last problem isn't simplified. You can't simplify.
It cannot be simplified? How do you know?
Because I divided 6,581 by every number from 0 through 9.
You divided 6,581 by every number?
Well, from 0 through 1, or 0 through 9. And nothing was divisible by it.
Oh, no, well, so far. It could be divisible by 11, 12, 13, 14. Yeah, so that's a tricky one.
We'll go to 20.
All right. Folks, let's keep going. We're on to section 9.4. I'd like to first just clarify something with you. The product rule for roots, and in fact, maybe even write it down up at the top to remind yourself. The product rule for roots stated that the square root of m times n is equal to the square root of m times the square root of n. We said that you can break up a root over multiplication. We also said that you can break up a root over division. That if you take the square root of a fraction, you can actually break that up into the square root of the numerator over the square root of the denominator. So both of those are valid operations, and it's referred to as the product rule for roots. Did we talk about whether or not there's a sum rule? Is it true that the square root of m plus n is equal to the square root of m plus the square root of n? Did we talk about that?
We did.
We did talk about it?
Yeah, we said no.
Yeah, we said no. That's not true at all. There is no sum rule. When you go to add roots together, you just can't add them together. That's not how it works. Did we give an example of that?
Yeah.
We did. I think we did the example of 16 plus 9, that if you wanted to add together 16 plus 9, that's really the square root of 25, which is really 5. Whereas on the other hand, root 16 plus root 9 is really 4 plus 3, which is 7. And so 5 is obviously not equal to 7. So this formula cannot be a formula that works. You can't just add roots together like that. So taking a look at the first problem here, can you just say that root 196 plus root 4 is root 200?
No.
No, definitely not. No, big no. You cannot just add the numbers together because you cannot just add roots in that way. Likewise, root 49 minus root 225, that wouldn't even make sense. If you just subtracted the numbers, 49 minus 225 is like negative, what? Negative 190, no, negative 176. But you can't square root a negative number. So again, you can't just subtract or add the numbers inside the roots. So if you can't do that, what are we to do? It says perform the indicated operation and simplify. How are we supposed to add root 196 plus root 4? First of all, everybody type it into your calculator. Do root 196, parenthesis, and then plus root 4. The answer might surprise you. What was the answer? 16. Yeah, the answer is just 16. Well, why is that? Do you recognize the 196? What's the square root of 196?
14.
14, and the square root of 4? 2. So 14 plus 2 is 16. So that's the answer. In this particular case, root 196 plus root 4 is easy to do because they both happen to be square rootable, and it's just 14 plus 2, which is 16. So what does that tell us about our strategy? In order to add roots, the first thing you need to do is look to see if you can simplify them. Right? Like root 196 is definitely simplifiable, so is root 4. So if you can simplify them so that they're not even roots anymore, then you're just dealing with whole numbers. So everybody do number 61. Yeah, as a general rule, if you can get rid of a square root symbol, that's your goal. If you can simplify a square root symbol, that's your goal. So what did we get? Root 49 is 7, and root 225 is 15. So the answer is negative 8. All right, well, that's not too bad. So long as they give you roots that can be simplified. Before we move on, we should put in our notes. Adding and subtracting radicals is like combining like terms. Go and write that down. Combining like terms. So first, you need to simplify. We'll see what that means here in a second. Adding and subtracting radicals is like combining like terms. The first thing you need to do is simplify. These simplified really nicely because they simplified all the way to a whole number. Well, let's look at the next couple. The next one is 6 root 11 plus 5 root 11. And so just for a moment, I want you to pretend that that's like me saying, I've got 6 root 11s here in my hand. 6 of them. I've got 6 root 11s. And I also have 5 more root 11s right over here. So how many total root 11s do I have? 11 root 11s. And that's the answer. The answer is just 11 root 11. And so I'm going to write that down here. Saying that I have 6 root 11s plus 5 more root 11s, I have 11 root 11s. That works the exact same way like combining like terms. If I had just said 6x plus 5x, what's 6x plus 5x? It's just 11x. So a root acts like a variable. It acts like a variable in the context that you're adding them together just like you would add variables together when you combine like terms. So in the next case, you have 6 root 17s, and then you take away 16 root 17s. How many root 17s do you have left? Yeah, negative 10 root 17s. Again, that's the exact same as if you had said 6x minus 16x. That would have been negative 10x. So what this tells us is that you can actually only add roots together if they're the same root. So as an example, can I add 3 root 7s plus 14 root 7s? Can I add 3 root 7s plus 14 root 7s? Yeah, because they're the same root. It's the like term. They're both root 7s, and so that answer is just 17 root 7s. On the other hand, what if I had 3 root 7s, and I'd like to add to it 4 root 10s? Can I add those together? Those you just can't add together. You just can't do anything with it. It's already simplified. It's done. It's just like had I said 3x plus 4y. Can you add 3x plus 4y? No. They're not like terms. You can't do anything with it. You just leave it there. You say, okay, that's it. That's as simple as I can get it. That's as simple as I can get it. Because they're not the same root. So that's maybe worth writing down. We can only combine like roots, as in like terms. So addition is a little harder than multiplication. Again, just to contrast that, if I said add root 3 plus root 5, you can't. You cannot add those together. That's the same as saying x plus y. You can't add those together. You're just done. The answer is just root 3 plus root 5. So you can't always add roots. Whereas multiplying roots, you can always multiply roots. Root 3 times root 5 is just root 15. That's what the product rule for roots states, is that you can multiply roots whenever you like. So if I had root 7 times root 3, it would just be root 21. Very simple. Root multiplication is just like normal multiplication. But as soon as I try to say root 7 plus root 3, there's no answer. It's already simplified and it's done.
What about division?
Division, you're allowed to divide as well. Like let's say that I had root 20 divided by root 2. That's just root 10. Yeah, you can multiply and divide roots to your heart's desire, and it just works like normal multiplication and division. You just can't add and subtract the way you would expect. So you are allowed to multiply and divide roots. You're not allowed to add and subtract roots unless they're the exact same root. And that's what we're about to see in this next triangle problem. It says, find the perimeter. So let me draw this up here real quick so we can all see it. I've got a triangle here, and it's 4 root 2, and then 3 root 18, and then 2 root 32. All right. First of all, is that a right triangle? Yeah, I mean, we have no idea. If you turn your head and look at that angle, does it look like a right angle? It doesn't even look like a right angle. These two definitely appear to be acute. That one appears to be bigger than the 90 degrees. It appears obtuse. And they didn't give us a right angle mark. So we don't know anything at all about whether or not it's a right triangle. Can we apply the Pythagorean theorem? What's that?
No.
Definitely not, because they didn't tell us it's a right triangle. And would we want to apply the Pythagorean theorem? Well, no, because they're just asking us to find the perimeter. And the perimeter just means what?
The sum of all sides.
You just add up all the sides. Okay, so this has nothing to do with Bob's theorem. It's just finding the perimeter. So can we add these? 4 root 2 plus 3 root 18 plus 2 root 32. Can we add them? No. Yeah, not like that. These are not, you cannot add them because the roots are all different. This is just like saying 4x plus 3y plus 2z. They're not like terms. They're not like roots. So you can't add them together. But what could we do? Like root 2, you can't simplify. But root 18, can we simplify it?
Yes.
What's 18 divisible by? 9. So we can actually break that one down. Let's do it. 3, that's root 9 times root 2. Right? Because 18 is just root 9 times root 2. 9 is a square number. Remember the process. We're asking what square number goes into 18. So I come up and I look, and 9 is a square number that goes into 18. So I rewrite that as 3 times root 9 is 3 times root 2. And that's really 3 times 3 is 9 root 2. So vertically, I just simplified 3 root 18 into 9 root 2. And look, bringing down my 4 root 2, now can I combine those two?
Yes.
Yeah. Well, let's not combine them just yet. Let's take a look at 2 root 32. Can we simplify root 32? Let's find it. What square number goes into 32? Yeah, 16 and 4, but which one do we want to use? Always the biggest one. We look for the biggest square number that goes in. So now you can write that as 2 root 16 times root 2. Again, that's the product rule for roots. You can rewrite a root as the product of two roots. So now that's 2 times 4 times root 2. And 2 times 4 is 8 root 2. And now look, they're all root 2's. This is the same as saying 4x plus 9x plus 8x. And so how many root 2's do we have altogether? 21 root 2's. Now, of course, what could we have done to solve the problem differently? We could have just plugged these into our calculator, couldn't we? We could have said 4 root 2 plus 3 root 18 plus 2 root 32, and it would have given us a decimal. I don't know what decimal we would have gotten, but we would have gotten a decimal. And then, when we're all done, we could have plugged this into our calculator, and that would also give us a decimal. And what would we have noticed about those two decimals?
They're equally.
Yeah, they're the same. They would have to be the same. Because all we did was we came up with a simpler way to write down the original sum. So that's a big deal. Take a look at how much better it looks. You want to find the perimeter of this triangle? Instead of writing down 4 root 2 plus 3 root 18 plus 2 root 32, all you have to do is write down 21 root 2. And that's the power of simplifying. It's a much simpler answer. Okay, so everyone, I'm going to give you some time here to work on the next one. What do we need to do first? They gave us a diagram of 4 root 24 and 5 root 6. What do we have to do first?
Make the top one 424, 5, 6.
Yeah, we need to finish labeling our diagram because after all, we're trying to find the perimeter. And the perimeter means add up all the sides together. So once you finish labeling your diagram, go ahead and write down a sum. Write them all down, add them all together, and you'll have to simplify. Well, you'll have to try to simplify root 6 and root 24. So go ahead and try that out. You'll write down 4 terms, simplify, and then see if you end up with the same like roots, like terms, and see if you can actually add them all together. And then you just plug that back in. Remember, you're going to do 24 would be, and you need to find a square root of either 16, 9, or 4. You can't use it.
24 is divided by 6.
It's got to be that one of them.
I know,
is
but
square.
6 and 4.
Yeah.
This side is 6. And 4 is square root of 2. And 4 is square root of 2. So 8 times 2 is 16.
Oh, that's the coefficient I'm talking about. It looks like, yeah, it's like a root. Did it work, Sino?
Oh, great. We just have to.
Yeah. Can we just add them, like the 2's, solve it together?
The ones that are already there?
Yeah.
Yeah. So folks, I saw a wide variety of approaches as I walked around the room, and that's great. Everybody had a slightly different approach. Some of you put the like terms next to each other, like the 5 root 6 plus the 5 root 6, and then the 4 root 24 and the 4 root 24. And then some of you had them alternating, like 5 root 6 plus 4 root 24 plus 5 root 6 plus 4 root 24. Either way is fine, because ultimately you still want to simplify these if you can. But if you write it this way, what can I immediately do? I can go ahead and add 5 root 6 plus 5 root 6, can't I? How many root 6's do I have? 5 root 6 plus 5 root 6. That's 10 root 6s right there. And then I have 4 root 24s and 4 more root 24s. So how many total root 24s do I have? 8 root 24s. So that's one thing I can do right away just to simplify my perimeter a little bit. But now I still need to try to simplify. So I look at both of them. Is 6 divisible by a square number? I look at where 6 would be, and is it divisible by 4?
Yeah.
It is?
No.
No. So that's not simplifiable. Number 6 is not, sorry, root 6 is not simplifiable. So that one's done. There's nothing we can do with root 6. But root 24, on the other hand, I look at where 24 would be, and I start dividing to the left. So 24 divided by 16 is a decimal. 24 divided by 9 is a decimal. 24 divided by 4 is 6. So I know I can rewrite root 24 as root 4 times root 6. And then I can do the square root of 4. That's 8 times 2 times root 6. That's 8 times 2 is 16 root 6. And then I drop down my previous number. That was 10 root 6. And now I have 10 root 6s plus 16 root 6s. And so did anyone else get 26 root 6? Now, there's a lot of different ways you could have done that. The way I showed my work up here might have been different from the way you showed your work. And that's okay, so long as we all end up with 26 root 6. Yeah. Any thoughts, questions about that? Or maybe did you do it differently and you want to know if it's okay? The other way you could have done it was to rewrite all of them. You know, you could have left the 5 root 6 and then the 5 root 6, and then you could have just simplified 4 root 24 once. So you could have said this was 4 root 4 times root 6, which is 4 times 2 times root 6, which is 8 root 6. And then I would have 5 root 6 plus 5 root 6 plus 8 root 6 plus 8 root 6. Did anyone do it that way, where you did them all individually? Yeah, that's totally fine. And then 5 plus 5 plus 8 plus 8 is still 26 root 6. So totally up to you folks. All right. Well, there's our adding and subtracting roots. Okay, well, that's it. That was section 9.4. It was all about adding and subtracting roots. So let's summarize that, folks. Can you multiply roots? Yeah, you can just multiply roots. A root times a root is a root. You can just go ahead and say anything at all, like root 7 times root 4 is root 28. So you're allowed to multiply roots. Are you allowed to divide by roots? Root 30 divided by root 6? Yeah, it's just root 5. Isn't that neat? So roots multiply and divide. But can you add, let's see here, 2 roots? And then the answer is no. Not unless you have like roots. So like root 28, I can simplify into root 4 root 7, which is 2 root 7. So now I really have the problem 1 root 7 plus 2 root 7. Now I can add them together as 3 root 7. So root 7 plus root 28, I couldn't do like that. I had to first simplify the root 28, and then once they were the same root, I could add them together. But you're not always guaranteed to be able to add 2 roots together. Sometimes it's just done. It just can't be simplified. All right. Well, that allows us to use addition and multiplication in the next problem simultaneously. Now we're going to practice FOIL with roots. And when you do FOIL, you're multiplying and adding. So that's a lot to keep track of. So is everybody here? What number is it for you, by the way? Oh, it is 66? Somehow we're back to normal? That's really weird. All right, I don't know how that worked. So here we are, number 66. We would like to multiply root 7 plus 1 times root 7 minus 1. First of all, can I add root 7 plus 1? No, they're not like roots, right? That's a root 7. That's just a 1. You can't add them together. You can't subtract them. So we just have to FOIL. So everybody, let's try it. FOIL. Let's take our time, show our arrows. F stands for first. So root 7 times root 7. I'm going to write them down rather than doing anything in my head. root 7 times root 7. So there's root 7 times root 7. That's my first. And then O stands for outer. So I have root 7 times -1. What's root 7 times -1?
-1 root 7.
Yeah, it's just -1 root 7. We haven't specifically said this yet, but a root times a root is a root, and a whole number times a whole number is a whole number. But a whole number times a root is just a whole number times a root. So you always put the whole number out front, and you put the root second. So root 7 times -1 is -1 root 7. You put the whole number out front. Okay, what about inner? What's 1 times root 7? Just 1 root 7. A number times a root is just the number times the root. You just write it down. You don't do a computation. You just write it down. And then finally, L stands for last. So 1 times -1 is -1. So look how fun a FOIL problem is. In FOIL, we're going to multiply a root times a root. We're going to multiply whole numbers times roots. And we're going to multiply whole numbers times whole numbers. So we're seeing the full spectrum of skills here. So what is root 7 times root 7?
Root 49.
Root 49.
Yeah, just root 49. You can multiply roots together. Roots multiply. So root 7 times root 7 is root 49. What about -1 root 7 and 1 root 7? These are like terms, so you can add them together.
They cancel out.
And they cancel out. So now we just have root 49 minus 1. And root 49 is?
7.
7. And so the answer is 6.
So when I have to put parentheses,
What's that, Sina?
when I have to put parentheses, like we always do in the part.
Do you have to put parentheses?
Like, you know, we did in
Oh, the cube thing.
yeah.
Oh, no, you don't have to do that. No. Sina was reminding us about the a cubed minus b cubed and how I recommended that you write it as a minus b. And then I said write it as parenthesis squared plus parenthesis parenthesis plus parenthesis squared. Sina, is that what you're talking about?
No, the to make it equals to 0, you have to put parentheses in the middle.
Oh, yeah, no, we're not doing the zero product rule because this isn't an equation. Yeah, we're not even solving for x. Is there a variable? There's no variable. There's no equal sign. We're not doing algebra. Yeah. All right, folks, let's try another one. Go ahead and let's try this one more time, and then we'll take a break. Root 3 minus 5 times root 2 minus 2. Very carefully do FOIL. And again, I really recommend you write it down one step at a time. So for instance, you would start by writing down root 3 times root 2. That's first. And then outer, -2 times root 3 is just -2 root 3. Those two things are being multiplied together. Okay, keep going from there.
So for this part, it would be -6. Yeah, the root 3 times -2. Yeah, because you're following the variable. Yeah, what you do with there is going to root times a whole number, and you can't multiply them. They just sit next to each other. So root 3 times -2 is just -2 root 3. Go ahead and write down -2 root 3. So you can see. Yeah, so roots and whole numbers are like oil and water. They don't mix. So if you're going to multiply root times a whole number, you can't. Just write them next to each other. Okay. So like the next step is inner. So you're going to have -5 times root 2. So you'll just write down -5 root 2. You can't combine those because they're not like terms. That's a root 3 and that's a root 2. So actually you're just done. You'll just be root 6 and then that. Great.
So finishing this one, we would do inner. -5 times root 2 is just -5 root 2. Again, just to clarify, you can multiply a root times a root, and you can multiply a whole number times a whole number, but you can't actually multiply a whole number times a root. You just write it down. So a whole number times a root, you just write it down. It's just -5 times root 2. The 5 and the 2 don't mix together. Okay, and then finally, last, -5 times -2 is positive 10. And what's the only thing I can do here? Yeah, the root 3 times the root 2. So I have root 6 minus 2 root 3 minus 5 root 2 plus 10. And if you wanted to be official or technical, that's a 1 root 6. So what I have here is a root 6, a root 3, and a root 2. Can I combine any of those together? No, they're all different. And that's it. That's your final answer. Very dissatisfying, isn't it? Sometimes I get so sad when something doesn't simplify. I'm like, oh, it doesn't simplify. But it doesn't simplify because they're not like terms. So that's your answer. All right, well, let's take a break. The time is 9:03. Let's come back at 9:13. Just in case, a little further reminder, did everyone bring me their quiz? Did everyone get a practice test? Okay, thank you. Oh, thank you. You did. Is what?
Well, I could have finished.
Oh, well, technically everyone's supposed to turn it at the beginning, but I think some people got here late. But when could you have finished?
No,
Yeah, the weekend, yesterday, this morning, the day before that.
forgot. Can I do half a credit after?
A what?
For the half a credit.
Are you going to do it late?
Late.
Oh,
Credit.
let me think about it. I typically do that for packets,
It's the same thing.
notes and whatnot.
Sorry.
Okay.
I was going to ask you for 59.
You were going to, but now you're not?
Well, I wanted to ask you for the answer because I remember back it says root 57, but you have to write 7 and just be 57.
What number?
Or 59.
Is that the same 59?
Well, yeah.
And so we're talking about the length of the diagonal of the box.
Yeah, just for the answer, I was thinking we have to write.
It's root 57, right?
Yeah.
Yeah. So what do you want to know?
That's the exact value.
Root 57.
It's root 57.
But we have to write the root.
Yes.
Maybe equals 57.
It's definitely not 57. What's the square root of 57?
So we can see.
Yeah, it's a decimal. Root 57 and 57 are not the same value. In fact, I would encourage you, Elda, there's only one number, actually there's two numbers in the universe where the square root of x is actually equal to x. But that only happens twice. So root 57 is not equal to 57. Root 10 is not equal to 10. Root 20 is not equal to 20. But there are two numbers in the universe where root x is equal to x. So maybe you want to find those two numbers.
Root x is equal to x.
Yeah, when is the square root of the number actually equal to the number itself?
That's 0, right?
0 is one of them,
And then E or I.
and 1 is the other one. The square root of I is actually not equal to I. I forget what it's equal to, but
Okay, thank you. I just thought.
Square root of I.
yeah, what
Isn't that just negative 1?
It's not. You're doing the square root of the square root of -1.
Okay.
Thank you very much.
Yeah, you're welcome.
I have to tell you this was. I was today. I have something. Okay, are you done?
Does the answer be back there?
Well, I was thinking, it's like. Oh, yeah.
That's nice, your calculator.
Oh, that one. I think that one will work. Yeah, your calculator does the I. Just sort of.
Sorry, I'm like, my chill is up. Yeah. 1.1.
Thanks, Paul.
What's the value for? So far, it's pretty simple. Or the instructors.
What was it, chocolate?
Yeah, for
5 or 6?
last year.
I think it was 6. Because but after that, chapter 7 was pretty much the same.
Those things are really first section.
Yeah.
That's another one I'm reading.
Is it on?
Jesus.
It's mostly on one side.
Yeah, that happened.
Like, she's like, oh, we're this and
On this one day.
Yeah, like some of the stuff are simpler. Because we just have to refresh it and just like get the copy.
That covers the one.
Oh, yeah, and then, yeah, I remember it sounds like the first second one.
Yeah, we have to do that like maybe every 2 weeks. I guess it's 2 months. Then get the days. And then for the chapter, which is not even hard because
Also, she gets you guys all the
yeah.
Oh, really?
But then we're doing what?
The answer sheets in the back are different.
Different from what?
Like number of
You like
68. Do you
I don't like it
think
either.
Nah, number 68.
Number 68, huh?
I don't like it that we're doing.
What answer?
I got 14 minus 5 root
Trying
8.
to.
And on answer sheet it's 14 minus 5 root 8 minus 8.
14 minus 5 root a minus a. That's what I got. 14 minus 5 root a minus a. 14 minus 5 root a minus a. Is that what they got?
Yeah,
What did you get?
I got just root 8. 14 minus 5 root 8.
Oh, but what about the a at the end?
But I thought they were canceling out. Oh, they don't.
What's root a times root a?
Because at the end, I thought you have to cancel it.
Sounds like a. Just to be good. And then we had to answer the question about what was as a, I can't wait till it's over.
Chemistry.
Yeah, I'm sure that's today.
No, on Friday.
This Friday or last week?
This Friday.
To retake your classes.
What exam is there?
What? Oh, this Thursday? Sheesh.
So much students.
We try to take 2.
Wait, we have an exam this Thursday?
No, next Tuesday.
Next
Next
Tuesday, bro.
Tuesday?
See?
I was like, what? This, I thought it was Thursday. Because
No, we have class this Thursday and then next week on Tuesday. I mean, you can always look at your syllabus. Your syllabus says the dates.
That's how we have to do like after writing the test.
Our class was just about vocabulary, just like some of the chapter.
What's what class is after this? 156, right? So it goes 130, 156, and then 181, something like that.
Well, you can take classes in many different orders depending on what your degree is.
So I don't have to take 156.
I don't know what you have to take and what you don't have to take. You don't have to do anything. You can go home right now. But I mean, no, I'm just kidding. But it depends on what your degree is and what your requirements are.
Mm-hmm. Yeah. Are you teaching? Because I'm taking 156 for the summer.
I'm not doing summer school.
But are you teaching 180 something?
I've never taught 180. That's Shannon Ruth, I think.
Is she good?
Oh, yeah.
Yeah. That might work for you. Gonna take nutrition class. Nutrition.
What's your GPA? I feel like mine's gonna go down. Okay.
Oh, I dropped a sub, but I got a W.
Bro, how do you freaking play it on mobile? I hate it.
Why?
It's freaking horrible.
All right, folks, let's keep going. I think everybody's back. So let's try a couple more of these together, just to make sure we all have a really good understanding of how it works. Come on back, folks. So where are we at now? 7 plus root A and 2 minus root A? All right, so we're still going to FOIL. And so first, 7 times 2. Again, whole numbers times whole numbers are whole numbers, so 7 times 2 is 14. And then outer, what's 7 times negative A? 7.
Negative
It's just negative 7 root A. So whenever you're multiplying a whole number times a root, you just write them down next to each other. There's no computation. You just write them down next to each other. Likewise, what's 2 times root A? Just 2 root A. You just write them down next to each other. You cannot multiply a whole number times a root. You just write them down next to each other. I mean, technically, they're still being multiplied. That is 2 times root A. There's a dot. And that's 7 times root A. There's a dot. You just can't merge them together into one thing. Okay, and then finally, what's a positive root A times a negative root A? That's negative root A times root A. But what's that? What's root A times root A? Yeah, root A squared. Because you can multiply a root times a root. So that's root A squared. So what do we have so far? 14. And we have minus 7 root A's plus 2 root A's.
5, negative 5. Yeah.
Minus 5 root A's. We can combine like terms right there. That's just like saying minus 7x plus 2x. So that's minus 5x. And then what is the square root of A squared? What happens to a square and a square root?
They cancel out, so it's just A.
Yeah, they cancel out. So we have 14 minus 5 root A minus a. And Sino, is that the answer in the back?
Yes.
Okay, good. Okay, number 69 I'll leave to you to do for homework, but let's just start it together. How do you square a binomial? Yeah, you have to write it down as two binomials. One of the most common mistakes that people make, probably because they're hurrying and not really thinking carefully about it, is people just try to square both of them. And they say, oh, the answer is 9 plus root 5 squared, which is 9 plus 5, which is 14. And that's all wrong. Then you could double check that it's wrong by plugging that into your calculator. So you can't just square them. What do you have to do? Write it down twice. Read plus root 5, read plus root 5. And then you do FOIL. So I'm just going to keep going. You can finish that one for homework. So let's take a look at the next section. All right. The directions say rationalize the denominator. Underline that phrase. Rationalize the denominator. This is really fun. Is it for me?
No.
Oh, okay. So rationalize. We talked previously about what a rational number is and what an irrational number is. And I believe we talked about how in mathematics we use the words rational and irrational very differently than common society. In common society, if you said someone's very rational, what does that mean? They're okay? You're okay. Yeah, it means they're sane, they're careful in their thinking, they're very straightforward, they make sense, they're rational. Whereas if someone's irrational, what do we think about them? Yeah, they're crazy, they make weird decisions, they're erratic, they're irrational, they do weird things. But that's not what it means in mathematics. What does rational mean in mathematics?
Divisible.
Not divisible. The root word is ratio. Ratio, like a fraction. A rational number can be written as a ratio of two whole numbers. Whereas an irrational number, what does the prefix ir mean? It cannot be written as a fraction of two numbers, such as pi, or the square root of 2, the square root of 3, the square root of 5. Basically, any root that cannot be simplified to a whole number. So that's just a quick review. That was many weeks ago that we talked about the difference between rational and irrational. A rational number can be written as a fraction of two numbers, such as 3, which is really 3 over 1, or 2/3, or even root 4. Root 4 is a rational number because root 4 technically equals 2, which technically equals 2 over 1. So a rational number is any number that can be written as a fraction of two whole numbers divided by each other. And one of the results of more modern mathematics, starting in the 1800s, is that pi is we've known that root 2 was irrational ever since ancient Greece, at the time of Pythagoras. I guess we've also known that pi was irrational as well. Okay, so we've known about irrational numbers for thousands of years, but they cannot be written as the fraction of two whole numbers. So that's the difference between rational and irrational numbers. So what do we now mean about rationalize the denominator? When do we use the word rationalize in common society? Yeah, to make sense of something, to make something normal. Or how do we more often use the word rationalize? Rationalize our decisions, to justify our decisions, like, yeah, yesterday I did eat an entire chocolate cake all by myself, but it was Easter, right? You know, like you make excuses for yourself. That's often what rationalize means. It means make excuses for something and make it sound better than it was. Like, it's okay, I did that because whatever. All right, but that's not what we mean in mathematics. What does rationalize mean? To turn it, I was going to say to make it, but to turn it into a rational number. So that's what we mean by rationalize in mathematics. It means to take an irrational number and make it rational. So just to give you an example, if I had the square root of 2, that is definitely an irrational number. It cannot be written as the fraction of two whole numbers. And one thing I could do to rationalize it is I could square it. Because what happens when I square a root?
It cancels out.
They cancel out and I get the number 2. And the number 2 is a rational number because I can write it as the fraction of 2 whole numbers. So that's one way you could rationalize a number. You could always just square it because that gets rid of the root. That's not at all what we're about to do, but I just wanted to give an example that it's possible to mathematically do something like, again, to say root 7. That's irrational because it can't be simplified to a whole number. And if I square it, they cancel out, and now I just have 7, which is rational. So that's what we mean by rationalize. It means to rationalize a number by changing it from an irrational number into a rational number. Okay, but specifically, what are they asking us to rationalize? Just the denominator. So let's talk about some party rules in mathematics. Some party rules in mathematics. I'm sorry, party rules. Party fouls. Party fouls. If you went into a math party and you said, hey, you all owe me, let's just say 15/30ths of a dollar. Would that be okay?
No.
That would be terrible. Would you really walk into a party and say, you owe me 15/30ths of a dollar? What would you say?
50 cents.
You owe me 50 cents, right? You'd want to be as clear as possible and communicate clearly. You'd really say half a dollar or 50 cents. But the main thing is that it's a party foul not to simplify fractions. Right? It's just rude. Like, you should simplify your fractions before you give that result to someone else, like in your audience. So that's one party foul. You always have to simplify fractions. What else do you have to simplify? Roots. So this is a new party foul that you just learned about within the last couple of weeks. If you have a root, you should simplify it. So you would take your root 20. You'd say, well, 20 is divisible by 4. So I'd rewrite that as root 4 times root 5, and I would get 2 root 5. And there, that's the answer you should give. So in terms of party fouls, you have to simplify your fractions. You have to simplify your roots. And these are just 2 expectations of you as a member of mathematical society. If you didn't do it, it would be a party foul. Okay, well, there's a new one. This is a third party foul. You cannot leave, this is your next problem, number 70. You cannot leave a square root in the denominator. You just can't. That might seem arbitrary and like a strange rule, like Mr. G, now you're just making things up. But it is a standard practice in mathematics that we don't leave square roots in the denominator. So right now, this expression is not simplified because there's a root in the denominator. What we want is a rational number in the denominator. Specifically, what we want is a whole number. Okay, so we have a preference in mathematical society, and that preference is whole numbers in the denominator. You're allowed to have roots in the numerator. That's just fine. You're allowed to have roots in the numerator, but you're not allowed to have roots in the denominator. This is just a party foul. There could be some deeply philosophical reason for this, and yeah, I think there are. But the main thing I want you to know today is just you can't leave a root in the denominator. So how do we get rid of it? Well, we can't just square that whole thing because that would change the value of the answer. Everyone type in 7 divided by root 6 on your calculator. What is 7 divided by root 6 if you get a decimal?
2.8577.
2.8577 something? Okay. So we still want to end up with a fraction whose value is 2.8577. So I can't just square the whole thing because then I would have 49 over root 6 squared, which would really just be 49 over 6. And that is no longer the same value. 6 goes into 49 a whole bunch of times. I think 8.166. So are we allowed to just square this whole fraction? No, that's not valid. I want to end up with another fraction whose value is 2.8577, and it just doesn't have a root in the bottom. Okay, so what can we do? What can we do? Hold on, I want to hear both of those ideas. Feza, say it again. Yes, that's one thing we could do, folks. We could multiply by root 6 on the top and the bottom. Why are we allowed to do that?
To lift up the square root on top.
Right, that would lift up the root on top. But what's root 6 divided by root 6?
1.
1. We're just multiplying by 1. And if I multiply 2.8577 times 1? I still have 2.8577. So I am technically allowed to do this because I'm just multiplying by 1. This thing still has a value of 2.8577. And so what happens? What's 7 times root 6? Just 7 root 6. You just write them next to each other. And what about root 6 times root 6?
Square root of 36.
Right, it's the square root of 36, which is 6. And there we've done it. We rationalized the denominator. That's the end of the problem. That's it.
I was just gonna say, you know how we in the other chapters, we just switch up the square root 6 up with the arrows.
Uh-huh.
Oh, we can just do that.
Wait, you want to do what with arrows?
Cause that, well, if it's with the negatives. For like the last chapter that we did the arrows, like pushing up the number and then pushing it down.
Oh, yeah, you mean like x squared over y to the negative 3, and you're allowed to push that upward? Well, that's a very interesting idea, Elda. I wonder if that's possible. I don't know. Nobody's ever said that before. I like your idea. We'd have to play around with it to see if that's even something that could be done. Not sure. Okay. Well, folks, so what did we do? First of all, I want you to confirm. Now type in to your calculator 7 root 6 divided by 6. You might have to do that in multiple steps. You might have to do root 6, enter, times 7, enter, divide by 6, enter. But I want you to see for sure that you still get the same answer of 2.8577.
Yeah.
Okay. So this technique, which I'll go ahead and write down, and maybe you'll write down at the top as well, or maybe I already wrote it down. Rationalize the denominator. Oh, no, we didn't. So rationalize the denominator. What a phrase, huh? What a phrase. That's a lot of syllables. Rationalize the denominator. Can you imagine yourself walking into a math party being like, hey, how's it going, everybody? What you guys doing? You're all rationalizing the denominator over here? What's going on? It's a nice phrase. So rationalize the denominator. You multiply top and bottom by the root in the bottom. Now, silly me, I just used the words top and bottom instead of numerator and denominator. I would have sounded more sophisticated had I said multiply the numerator and denominator by the root in the denominator. But I find the word top and bottom is quicker and easier to say. So that's our method. If you want to rationalize a denominator, you have to multiply the top and the bottom by the root in the bottom. And that has the effect of canceling out the root in the bottom. And folks, you might just want to make a little note right here. What happens anytime you multiply a root times itself? In general, which is what's always going to happen, right? We're multiplying a root times itself in the denominator. What happens anytime you multiply a root times itself?
Just cancel
It just cancels it out, and the answer is x. So for instance, root 13 times root 13 is 13. And root 2 times root 2 is just 2. And root 58 times root 58 is just 58. That's something handy to just memorize, that a root times itself is just the number. And why is that?
You can prove it.
Yeah, you can prove it. Root x times root x is really root x squared. And what happens to the square and the square root symbol? They cancel out and you just get x. Okay, so this is a whole technique called rationalize the denominator, devoted to the idea that mathematical society just has a preference not to leave roots in the denominator. That's it. It's just a party foul. Technically, 7 divided by root 6 and 7 root 6 over 6, they represent the exact same decimal value of 2.8577. We just prefer to not have roots in the denominator. So let's try another one. This next one might look a little more sophisticated. Root 81 over 28. Technically, is the denominator being square rooted?
Yeah.
Yes, because the whole fraction is being square rooted, so technically the denominator is being square rooted. Well, what's the first thing we can do?
Cancel out the.
Yeah, we want to do the root of the top and the root of the bottom. That's one thing we're allowed to do, is break up a root over a fraction. And that's very convenient because what happens to the numerator? Yeah, that's just 9.
Sorry.
Okay, so there it is. We can clearly see we have a root in the denominator. We'd like to get rid of it. The method says multiply top and bottom by the root in the bottom. So what do?
Multiply it by 1.
Yeah, multiply times root 28 in top and bottom. So then what do we have? What's 9 times root 28?
9 root 28.
Just 9 root 28 all over 28. So we did it. We rationalized the denominator. Are we done with the problem? Why not, Raymond? Yeah, party foul number 2. So party foul number 1, you have to simplify fractions. Party foul number 2, you have to simplify roots. Party foul number 3, you have to rationalize denominators. So we did rationalize the denominator, but we can still simplify the root. It always in general, folks, you have to look at any root that's in your final answer and check, can I simplify it? So there's 28, and is it divisible by 25? No. Is it divisible by 16? No. Is it divisible by 9? No. Is it divisible by 4? Yes. So we would now have to break that root 28 into root 4 times root 7. Right, because root 28 is equal to root 4 times root 7, which gives us, 9 times 2 times root 7 over 28, which is 18 root 7 over 28. Oh my gosh, folks, this is such an exciting problem because all 3 party fouls are in play. The first party foul was that we wanted to rationalize the denominator, so we did. The second party foul is that we had to simplify the root 28, so we did. And what's the last party foul? You have a fraction here that can be simplified, 18/28. So what can we divide out of 18 and 28? 2. So now that's 9 root 7 over 14. Wow, what a great problem. I never realized that all 3 party fouls were in that one problem. So we had to rationalize the denominator, which we did. We had to simplify this root, which we did. And we had to simplify this fraction, which we did. So the final answer is 9 root 7 over 14.
You didn't put in a negative.
Hmm?
You didn't put a negative.
Oh, you're right. There's a negative sign in front, so the final answer is negative as well. Now, folks, I'm not sure what you're thinking right now, but there's a possibility that part of you is thinking, who cares? Like, what's the difference between root 81 over 28 and 9 root 7 over 14? Like, take a look there. We just did a whole bunch of work to show that root 81 over 28 is the same as 9 root 7 over 14. And you might be saying to yourself, aren't they both just as good? Like, why did we all do all that work when both of these have the same decimal value? And you could test that for yourself. Do the square root of 81 divided by 28, get a decimal. And then do 9 times root 7 divided by 14, get a decimal. Will you get the same decimal? Yes, you will. You'll get the same exact decimal.
I have a question.
Yeah.
Can I break down 29 to the beginning?
Can you break down
28.
in the beginning?
Yeah.
Oh, yeah, you sure could. If you wanted to have broken that down in the beginning, you could have.
And that's the same answer.
Yeah, you'll get the same answer and everything. Everyone, listen to Fez's idea. She wants to take 9 over root 28 and immediately simplify the root 28. So what does root 28 simplify to? 2 root 7? 2 root 7? So she could have immediately said that's 9 over 2 root 7. And then right there, you could rationalize the denominator just by multiplying root 7 on top and bottom. So now Fez would have root 7, and that would give her 9 root 7 over 2 times 7. Because root 7 times root 7 is just 7. And that would give us 9 root 7 over 14. Fez, is it the same answer? Yeah. So sure, Fez, if you want to, you can simplify the root earlier on. That's totally up to you. Okay, everybody, try the next 2. Do those on your own. Rationalize the I think you noticed that these two went a little faster. There really wasn't much to simplify here. So 9 over root 2, who'd like to do this one? How about Amber? What do I do? Yes, you do. And then what do you get in the numerator? Yep, that's it. 9 root 2 over 2. That's called rationalizing the denominator. It's just a preference in mathematical society to do that. And then what about 4 over root 11? What do you do, Sienna? Yeah, root 11 top and bottom, and what do you get? Yeah, 4 root 11 over 11. All right, folks. So there's one more skill before we get into solving equations, which is really fun, and that's rationalizing the denominator when the denominator is not just a single root. It's not just a single root. So for instance, what are these denominators? What do they consist of? Yeah, there's an addition problem or a subtraction problem going on. You've got a root and a whole number down there. Or in the very last one, 2 roots in the bottom that don't combine. So we still have this mathematical party foul that says don't leave a square root in the denominator. So there's a root 6 down there, we want to get rid of it. And here there's a root 7, we want to get rid of it. And there's a root 2, and we want to get rid of it. And here there's a root 5 and a root 3, and we want to get rid of it. Again, strictly for the sake of following this mathematical party foul, which is don't leave roots in the denominator. So let's just do maybe 1 or 2 of these together and then move on. So number 74, we start with 7. Oh, I'm sorry, 4. Oh my gosh. I did write 4, okay. 4 over 9 minus root 6. Well, we can no longer just multiply top and bottom by root 6. Don't write this down. But if you just multiplied by root 6 on top and bottom, you would end up with 4 root 6 on the top. And then on the bottom, you'd have to distribute the root 6. And you would get 9 root 6 minus root 6 times root 6 is 6. And you would still have a root in the denominator. So did that work? No, we had a root 6. We still have a root 6. We didn't get rid of the root 6. So if there's an addition or subtraction problem in the denominator, we need a new technique. A new technique. And so what is that new technique? Up at the top, you can see it says, in order to rationalize a binomial denominator, oh, doesn't that sound good? Rationalize a binomial denominator. You must multiply the top and bottom by the conjugate of the denominator. So let's remember what conjugates are. A conjugate, you have seen conjugates before. Conjugates are a plus b and a minus b. We've seen that before because the formula for difference of squares, a squared minus b squared, is a plus b times a minus b. And I think we have previously referred to those as conjugates. Have we seen this vocabulary word before?
Yes.
Okay, so conjugate just refers to 2 binomials that are exactly the same, except one is plus and one is minus. So that is what is meant by a conjugate. Same numbers, one is plus, one is minus. So it says here, in order to rationalize a binomial denominator, you must multiply the top and bottom by the conjugate of the bottom. So what's the conjugate of the denominator here, Rob?
9 minus square root of 6.
What's the conjugate of that?
3.
Conjugate just means one is plus and one is minus. So you'll just change the minus sign to a plus sign.
Oh, okay.
So the conjugate is?
So you'd still write 9 minus square root of 6, and then, or would you just, oh, it would be the 9 plus square root
9 plus root 6. So everybody go ahead and multiply the top and bottom by 9 plus root 6. So the conjugate of 9 minus root 6 is 9 plus root 6. And so that's what we're going to multiply on top and bottom. That's the method.
Do we just distribute the 4?
Yep. Yep. So this is actually quite a bit of work. You know, it takes more than 2 seconds. You're going to have to distribute the 4 across the top. The numerator is nice and easy, so you might want to do it first to feel good about yourself. So 4 times 9 is 36, and 4 times root 6 is 4 root 6. The denominator will take a little more time, but just a little more time, because we have to FOIL conjugates. Now, maybe you remember from last time. What happens when you multiply conjugates?
The middle cancels.
Yeah, something special happens. The middle terms cancel out. A times A is A squared. Then you have minus AB. Then you have plus AB. And then you have minus B squared. When you multiply conjugates, the middle terms always cancel out. So let's see that happen with the roots. When you do FOIL, you have 9 times 9, that's 81. Then outer, you have 9 times root 6, which is 9 root 6. And then you have inner, 9 times negative root 6, which is negative 9 root 6. And then you have last, negative root 6 times positive root 6. A negative times a positive is negative. Root 6 times root 6 is just 6. That last step you might want to see again. What's root 6 times root 6?
That is negative 36.
Yeah, it's negative root 36, but the square root of 36 is
6.
Just 6. And like I said earlier, a root times itself is always just the number. So root 6 times root 6 is just 6. So that last part is just minus 6. All right, so there we go. We FOILed the denominator. What happens to our middle terms?
Cancel.
They cancel out. How convenient. So we're left with 36 plus 4 root 6 all over
75.
81 minus 6 is 75. Notice that we accomplished our goal. Is there a root in the denominator anymore?
Nope.
No. So we started with a root in the denominator. Now we don't have a root in the denominator. And that root, where did it show up? In the numerator. So Elda mentioned earlier the whole idea of pushing things from one side to the other. I mean, we didn't really use that technique like before, but it is definitely like a wrinkle in the carpet. Like if you ever have a wrinkle in your carpet, you can try to push it one way or the other, but you're still going to end up with a wrinkle. Have any of you ever had a wrinkle in the carpet? Maybe you have, maybe you haven't. Okay, well, yeah, I mean, the root 6 isn't going to go away completely. We just got it out of the denominator and into the numerator.
Quick question.
Yeah.
Should we simplify the 36 and 75?
Can you simplify 36 and 75?
Dividing them by 3.
No, these whole numbers are not simplifiable.
Oh, okay.
Yeah, 4, 36, and 75 aren't all divisible by anything. So you're just done there. Folks, I only have a couple minutes left, and I want to at least suggest the idea of where we're going. So we're going to turn the page, and let's take a look, and maybe we can do one, if not 2 of these. This is actually what we spent the whole chapter leading up to. We spent the whole chapter leading up to the ability to solve equations, right? That's the whole point of algebra. The whole point of algebra is to have an equation with a variable in it and to solve for the variable. So now that we have a really good, thorough understanding of how square roots operate, we can go ahead and solve for this formula right here. So root 4q minus 3 equals 3. So keep in mind what we always mean when we say solve an equation. What are we trying to find? Yeah, we're trying to find q, and what happens if we find the correct value for q?
Should make it true.
Yeah, should make it true. So we're looking for a value for q that we can plug in right there and somehow make this thing equal 3. Now we could probably take a guess, right? What would have to be under that square root symbol for it to equal 3? The square root of what is 3?
9.
9, right? So we know that that better equal 9. And so we could solve that real quick. When is 4q minus 3 equal to 9? Well, that's 4q equal to 12, which is q equal to 3. So apparently if I plug in 3, it should work. Let's try. If I do the square root of 4 times 3 minus 3, will that equal 3? Well, that's the square root of 12 minus 3. Will that equal 3? That's the square root of 9. Is that equal to 3? Yes, that's true. So the answer then, if you want to go ahead and write it down, q equals 3. We know that's the answer. That's not how we're about to solve it. I just wanted you to see, again, the purpose of algebra is to find a number that if you plug it in, it makes it true. So we already know the answer is 3. So how do we find the answer the legitimate way?
You square both sides first.
Yeah, we square both sides first. Let's remember algebra, we want to get q by itself. And right now, q is being multiplied by 4, subtracted by 3, and square rooted. And what's the opposite of square rooted? Square it. So the first thing we'll do, folks, go ahead and let's all do it together, is square both sides. What happens when you square both sides?
The square root cancels.
Yeah, the square root and the square cancel. And now we just have 4q minus 3 equals 9. And actually, this is the algebra problem I just solved a second ago. So now you just do traditional algebra. You add the 3 over. You get 4q equals 12. Divide up to 4. And q equals 3.
I was thinking -5 plus 3 and then.
Okay. So you can't add the 3 until you get rid of that square root symbol. Yeah. Now, folks, we might as well look, I wrote here, solving equations with radicals. Remember, when the root is part of the equation, you're always looking for the positive square root. Okay, so let's take some notes. When the root is part of the equation, you're always looking for the positive square root. So if I said the square root of 25, I really mean just 5, positive 5. Not plus or minus 5, but just positive 5. More importantly, solving equations with radicals. Let's write down our general strategy. The general strategy is isolate the root, and by that I mean get the root on one side of the equation by itself. Isolate the root, that means get the root on one side of the equation by itself, then square both sides. So just to clarify this word to isolate, isolating the root means getting it alone on one side of the equation by itself. Is this root isolated?
Yes.
It is isolated. It's on one side of the equation all by itself. Look at the next one. Is this root isolated? No, there's a -4 on the left-hand side of the equation with the root. So this root is not isolated yet. If the square root itself is not alone on that side of the equation, there's a -4 there. So we'd have to move the 4 over first before we could square both sides. This one is already isolated. Take a look at the next problem. I know you have to go. Is this root isolated?
No.
No, there's a +3 next to it. Is this root isolated? No, there's a whole other root next to it. So our goal is going to be to get the root by itself, and then you can square both sides. Okay, I know you gotta go. I have visions of just keep going and like checking to see what you guys would do if I just kept going and going. Like, would you finally awkwardly get up and leave, like one person at a time, or would you just roll with it? I mean, I'm really curious. Social experiment.